Hello, class. Well, if you're seeing this video, you've got the link to it. It means you're in one of my astronomy classes, or one of them shared the link with you for whatever reason. We are going to uh, go over the PowerPoints that we missed out on Monday because it was Labor Day. In order to catch up, this is necessary, and this is actually very important material. If there are questions about it that come up during class, I will have to refer you to the video. Without further ado, the moon, our constant companion. So let me start the PowerPoint from current slide. So our goals for learning are: why do we see phases of the moon and what causes eclipses? So lunar phases are a consequence of the moon's 27.3-day orbit around Earth. Usually we treat it like a 28-day cycle, but it's not exactly 28 days. It's not even really that close to 28 days. The moon orbits the Earth basically once a month. A half moon is illuminated by the sun and is half dark. We see a changing combination of the bright and dark faces as the moon orbits the Earth. That said, only one side of the moon faces us at any given time. The moon rotates on its axis as it revolves around the Earth, and it turns on its axis once for every revolution. So there's never a time when from Earth we can see the far side of the moon. So a new moon means we don't see it at all. A crescent moon, first quarter, gibbous moon, full moon, another gibbous moon, last quarter, and crescent. When it's waxing, we're seeing more of it. When it's waning, we see less of it. So consider it's 9 a.m. You look up in the sky and see a moon with half its face bright and half dark. What phase is it? When questions like this come up, it might be a good idea to pause the video and try answering them. The third quarter. So we only see one side of the moon. Synchronous rotation, the moon rotates exactly once with each orbit. You will face so you have a model of the Earth and you walk around it, you'll face the model once, or you'll face the same side of you will face the model as you go around it. Now, a simple way to illustrate this that I would do if we were in class is to go ahead and walk around my desk. But since we're not in class, let me show you a different thing for me to walk around. So this is a pole that I use for exercise and just for fun. So one side of me is always facing this, but I'm also spinning on my axis. See? So for every time I go around, I turn one full revolution around. Now I can show you that. Let's say I take this stick and put it here on top of my head, right? So I'm facing that way, and as I go around the pole, the stick points in every direction because I'm also turning on my axis. That's essentially what this slide is trying to tell you. So that's why we only ever see one side of the moon. We didn't see the far side of the moon until the lunar explorations of the 1960s. An eclipse, such as this would be a lunar eclipse, is when the Earth casts a shadow on the moon. We see a lot more of those in this part of the world than we do of solar eclipses. So here we have the sun shines on one side of the Earth, the moon moves through Earth's shadow, and we see a lunar eclipse. So a shadow like that of the Earth has a couple of parts. The umbra, which is sort of a partial shadow, and the penumbra, which gives us a full shadow or a total eclipse. Solar eclipses are much rarer in this part of the world, but they do happen. There was one several years ago, and there'll be one a few years in the future. So a solar eclipse is when the moon moves in front of the sun and it casts a shadow on the Earth. The penumbra of that eclipse gives us a total solar eclipse, and that's usually a narrow path of totality. Here's a total solar eclipse in Zambia. Solar eclipses can occur only at new moon. Solar eclipses can be partial, total, or annular. The reason solar eclipses only happen at new moon is because they have to happen when it would otherwise be daylight. Why don't we have an eclipse at every full and new moon? Now, what this slide is pointing out, the Earth and the moon don't orbit in the same plane. The plane of the moon's orbit around the Earth is off the same angle as the plane of the Earth's orbit around the sun. The Earth's orbit around the sun is called the ecliptic, and the orbit of the moon around the Earth is at an angle to the ecliptic, so it doesn't eclipse every single month. It must be a full moon, and the moon must be at or near one of the 2 points in its orbit where it crosses the ecliptic plane, its nodes. Eclipses recur with the 18-year, 11 1/3 day Saros cycle, but the type, partial, total, and location may vary. So we had in 2017 the Great American Eclipse. It traveled from east to west and passed over Carbondale, Illinois. The center of the path was actually several miles to the south of Carbondale. I traveled down there for that. That same point will be crossed over by the eclipse in 2024, which will travel from from north to south. Why do we see phases of the moon? Half the moon is lit by the sun, half the moon is in shadow, and its appearance to us is determined by the relative positions of the sun, moon, and earth. A question you could have in your mind is, do we see, or if it was lit up, would we see the far side of the moon when it's in shadow, when we only see part of the moon? And the answer is no. The only side of the moon that ever faces us is that near side, just as only this side of my body was towards the pole. What causes lunar eclipses? A lunar eclipse is the Earth's shadow being cast on the moon. Solar eclipse is the moon casting a shadow on Earth. So why was planetary motion so hard to explain? And why did the ancient Greeks and others reject the real explanation for planetary motion? So these are the planets that were known in ancient times. These are the naked eye planets. Mercury is difficult to see because it's always close to the sun. You can really see it in daylight, at daybreak or sunset. Venus, very bright when visible, the morning or evening star, and also responsible for a lot of UFO sightings. Venus looks to be this big pulsating thing in the sky because of its very bright clouds. Mars is noticeably red. If you were to go outside on a clear night and look up right now, you would see a very bright red spot, brighter than usual because it's on its closest approach to Earth for the next 15 years. Jupiter is very bright, and Saturn is moderately bright. We didn't know Saturn had rings until Galileo looked at it through a telescope. Planets usually move slightly eastward from night to night relative to the stars, but sometimes they go westward relative to the stars for a few weeks. This is called apparent retrograde motion. So with the heliocentric model, we can very easily explain the retrograde motion. It's simply a matter of the relative position between Earth's orbit and Mars' orbit, for example. As Earth is going around on sort of an inside track, Mars will appear to go backwards. Or it will appear to go backwards for a while, circle around, and then proceed forwards. These circles around were explained in the geocentric model using something called epicycles. So why did they reject the heliocentric model? Part of it was because they couldn't really understand how far away the stars were. They couldn't observe stellar parallax. Stars are so far away that the stellar parallax is too far to notice with the naked eye. A way of getting an idea of what parallax is, for example, try looking at your nose. That's the easiest self-demonstration you can do. You'll notice when you look at your own nose, you see what appear to be two different images offset a little bit. Also, hold your hand out in front of your face. Even with it directly in front of your face, you'll notice it blocks different things in your field of view depending on which eye is open. It seems like a ridiculous demonstration. You're sitting there, why is this person doing this? But try it. Hold your hand out and notice that with one eye, one thing will be blocked by your hand, and with the other eye, a different thing will be blocked by your hand. It's the same thing going on here. Those two positions of Earth in July and in January, about 6 months apart, those are like your two eyes. We can't be in both places at the same time. So we take one picture, then we wait 6 months, take another picture, and we can see that some objects will appear to move against the apparently fixed stars. In fact, all of them will appear to move. The question is, do we have the angular resolution? Can we resolve that little tiny angle? So, like the sun and moon, the planets usually drift eastward relative to the stars, but then there's also the apparent retrograde motion. And they concluded Earth must be stationary because they couldn't see the stellar parallax. Now, let's move on to chapter 3, at least a little bit here, the Science of Astronomy. So, in what ways do all humans use scientific thinking? How is modern science rooted in ancient astronomy? Scientific thinking is based on everyday ideas of observation, trial and error experiments. For example, by this point you have all tried using stellarium in class. The only real way to learn how to use that is not to have somebody else hold your hand and click the buttons for you, but to just press all the buttons and see what they do. In a way, pressing all the buttons on a computer program or a device and seeing what they do is science. It's trial and error, but a very organized trial and error. Astronomy is used for keeping track of seasons, aiding in navigation. It was the original clock and the original calendar and the original map. So the seasons could be predicted from the orientation of the crescent moon, for example. Days of the week were named for sun, moon, and visible planets, uh, many of them named for various gods in whatever culture. I happen to name them. In the West, we have Germanic, Greek, uh, French, Spanish names. So Sunday is Domingo, and Dimanche in France. Monday is just Monday, it's Moon Day. Lundi, and Lunes in Spanish. The Spanish and typical names for it, as well as the French names, will sound very similar because a lot of the English words for them came from Latin, and French and Spanish are Latin-based languages. So Saturn, Sabado; Venus, Verendi, Verenes; Jupiter, Jude, Juves; Mercury, Mercede, Miricoles; Mars, Mardi, Martes, etc. Whereas English has Germanic words in it, so Tu for Tuesday, Woden for Wednesday, Thor gives us Thursday, Freya gives us Friday. What did ancient civilizations achieve in astronomy? Things like daily timekeeping, tracking seasons, monitoring lunar cycles, predicting eclipses, and more. One of the things that came out of that was the idea that they could predict who should marry who, what would be a good day to go into business, and that became astrology. Sundials, a very ancient astronomical tool. Basically, the idea is the sun would mark out 12 hours a day by making 12 equal marks. Problem with using a sundial is, unless you're at the equator, the length of a day changes with the year. So some days you could have very long hours, other days you could have very short hours. Stonehenge, circular calendar. That's what we believe it was used for now. Of course, that civilization, that group did not leave any written records, so we can pretty much guess. But similar henges exist all around the world. For example, here in the Midwest, there are Native American wood henges that have been found. These wood henges would start out with just a pole put up in the ground, and then the shadow it had on certain auspicious days would be marked off. Over time, important people would be buried at the base of the pole, and as these burials would build up, you could build up a basic mound, and whole entire cultures called the mound builders, the Mississippians of Native Americans, existed, and astronomy seems to have been very important to their city planning. In Mexico, this reached a very high expression in the form of their stone pyramids, like the Templo Mayor. The plaza that the Templo Mayor stood in front of still exists in Mexico City to this day. Of course, pyramid's not there anymore. New Mexico and Anasazi Kiva aligned north to south. And a sun dagger marks the summer solstice. Scotland, 4,000-year-old stone circle, moon rises here every 18.6 years. And in Peru, the Nazca lines are aligned with the stars. Machu Picchu in Peru, structures aligned with solstices. In the South Pacific, Polynesians were very skilled in the art of celestial navigation. That is a star map. And cave paintings from 18,000 BC may suggest a knowledge of lunar phases. China gives us some of the earliest known records of a supernova from 1400 BC. So what have we learned? In what ways do all humans employ scientific thinking? Basically, trial and error. How is modern science rooted in ancient astronomy? It's one of the oldest sciences, if not the oldest of the sciences, and it's important. Practically, civilizations used it to know when to plant, when to harvest. They used it to know uh, where to build and to keep time. It also was useful for navigation. So the ancient Greeks. So mathematical and scientific heritage originate with the civilizations in the Middle East and Mesopotamia. It's, as has been said, all humans use scientific thinking. Um, Obviously, a lot of math had to be worked out in order to build things like pyramids and align them to the stars as they appeared at the time. A lot of math had to be worked out to build the ziggurats of the Sumerians and Babylonians, and so forth. In the Western world, traditionally, scientific thinking is traced to the Greek philosophers. Uh, so, and those Greek philosophers existed in the Hellenistic period. The Hellenistic period of Western civilization began when Alexander the Great took over much of the world, from ancient Greece down into Egypt, all the way to the part of the Indian subcontinent now known as Pakistan and Central Asia. He spread Greek culture and Greek ideas throughout that entire area and brought all of the ideas from that very wide and very long civilized area together. It was during the Hellenistic period that Alexandria was founded, named after Alexander the Great. The Library of Alexandria was built by his successors there, the Ptolemies. That includes everyone from Ptolemy I, who was one of Alexander's generals, right through to Cleopatra of the same fame as who knew Julius Caesar. Fun historical fact: some people imagine that Cleopatra and King Tut knew each other. Cleopatra and King Tut are further apart in time than we are from Cleopatra. And King Tut is further apart in time from Cleopatra than is further from Cleopatra than he is from the pyramids. So ancient Egypt spans a very, very long period of time. Most of recorded human history has some part of it recorded in ancient Egypt. But it was really with the Hellenistic period that began modern science as we think of it. At least the philosophies that would become modern science, mathematics, geometry, algebra, all of that, drawing on all of that collected knowledge that existed before. One of the things that made ancient Greek science different from what came before it was the idea that things could be understood rationally, whereas earlier civilizations tended to attribute all knowledge to gods or to divinity, even things like mathematics. Now, there was some elements of that that still went on with the ancient Greeks, for example. There was an idea that mathematical geometric shapes were perfect, and you could derive everything from those. So Greeks were the first known to make models of nature and then try to test those models against what they observed without resorting to the myths or the supernatural. So Eratosthenes measured the Earth's circumference by taking a stick, much like this one, and placing it, a stick of known height, and measuring the shadow that it casted. He did that at two widely separated places, and he was able to measure the diameter and circumference of the Earth. The circumference of the Earth, and from that, of course, you know, the diameter and the radius. So people already knew, thanks to people like Eratosthenes, that the Earth was round hundreds of years before Christ was born. At least educated people did. And they knew approximately how big it was. So Plato and Aristotle, they gave us the geocentric model that was eventually became such deeply held knowledge that even churches thought that it was in the Bible. No such thing is true. Earth is at the center of the universe. Heavens must be perfect objects, move in perfect spheres or in perfect circles. The idea was that objects in heaven were perfect spheres of ether, and these ethereal objects moved in circles because it was their nature to. Heavy objects like this fell because they had earth in them, and it was the nature of earth to fall, for example. This made it difficult to explain things like retrograde motion. So the geocentric model, a very sophisticated one, was the Ptolemaic model, and it was accurate enough for everything they observed for 1,500 years. So the Ptolemaic model explains retrograde motion by saying that the planets will sometimes move on epicycles. When it's going in retrograde motion, it's moving on its epicycle. Pause and see if you can answer this question. The geocentric model is useless for predicting planetary positions in the sky, whereas even the earliest sun-centered models worked almost perfectly. So this is not a fundamental difference between the geocentric and sun-centered models. The geocentric model was not useless. If it was useless, no one would have used it. The geocentric model is simply more complicated. We can explain everything with a simpler model and explain even more with that simpler model. The Muslim world preserved and enhanced the knowledge they received from the Greeks while Europe was in its dark ages. Remember, the Muslim world, if you think of what that Hellenistic world was comprised of, Egypt, Middle East, areas that are now Iran and Pakistan. So when Islam came to be, when it was revealed in around 600s AD, and the Umayyad Caliphate conquered everything from Spain to Pakistan into Central Asia and much of Asia Minor, they actually inherited much of the civilized area that was the Hellenistic Greek world. And one of the intellectual pursuits of the day was to copy and translate Greek text into Arabic. The other thing that period gave us are actually the Hindu Arabic numerals we use. 800 and 1453. Those actually come from India by way of the Muslim world. Al-Mamun's House of Wisdom in Baghdad was a great center of learning in around AD 800. Baghdad was a great center of learning until it was conquered and sacked by Hulagu of the Mongol Empire. With the fall of Constantinople, Istanbul, in 1453, Eastern scholars headed west to Europe, carrying knowledge that helped ignite the European Renaissance. Scholars that were connected with the Islamic world also existed in Spain, as Spain spent 800 years in some part or the other being ruled by Muslims, and the Reconquista, the full reconquest of it, concluded in the early 1490s, around the same time as Columbus was reaching the New World. Why does modern science trace its root to the Greeks? They developed models of nature that didn't resort to myth. The Ptolemaic model had each planet move on a small circle called an epicycle. The Copernican revolution. So how did Copernicus, Tycho Brahe, and Johannes Kepler challenge the Earth-centered model? What are Kepler's 3 laws of planetary motion? How did Galileo solidify the Copernican revolution? So Copernicus, Tycho, and Kepler challenged the Earth-centered model. Copernicus proposed a sun-centered model published in 1543. He used the model to determine the layout of the solar system. But the model was no more accurate than Ptolemaic model in predicting planetary positions because it still used perfect circles. So what are they saying? Copernicus's model had the sun at the center and drawing the most perfect circle I can, which is not very perfect at all, these circular orbits, right? But actual planetary orbits are not exactly circular. Tycho Brahe compiled the most accurate 1 arc a minute naked eye measurements ever made of planetary motions. He still could not detect stellar parallax, so thought the Earth must be at the center of the solar system, recognized other planets go around the sun. He hired Kepler, who used Tycho's observations to discover the truth about planetary motion. Tycho actually also compiled data from other observations, other star maps, other troves of um, uh, knowledge from China to the New World to the Middle East to Europe and refined them with his own. So he not only observed, he compiled and condensed a lot of information in order to make the most accurate possible maps. Johannes Kepler, so he tried to match Tycho's observations with circular orbits, but an 8 arc minute discrepancy led him to eventually to ellipses. So if the sun is here, basically he has the planets orbiting like so. So they're more elongated ellipses, like so. So in an ellipse, you have these two foci, and the distance, this distance right here, from there to there, and come on, oh, from there down to there, and this distance from here down to here are the same distance. That's more or less what defines an ellipse. An ellipse looks like an elongated circle. Sometimes students call this an oval. The word for it is an ellipse. An oval is not exactly the same thing. Kepler's first law, the orbit of each planet around the sun is an ellipse with the sun at one focus. There is nothing at the other focus. Now, very few orbits are that stretched out. An orbit like that would probably be a comet, not a planet, but Kepler's first law, the orbit of each planet around the sun is an ellipse with the sun at one focus. It will be a very low eccentricity ellipse, very close to being a circle, but not quite. Kepler's second law, as a planet moves around its orbit, it sweeps out equal areas and equal times. So those two areas are the same. Kepler's third law, the more distant a planet's orbit, the more distant planets orbit the sun at slower average speeds, obeying the relationship p squared equals a cubed. The square of the period is equal to the cube of the semi-major axis. Average distance from the sun in AU. So this is good enough. There are more precise statements, but that's good enough. So a question you might have if you're asked to solve for one of these variables, let's say you're asked to solve for the period given the average distance from the sun, or the average distance, like say you have planet X and let's say instead of the sun and the earth, you have planet X and moon M sub X, right? And the problem you have says that the center of mass of planet X is a distance r from the center of mass of moon M sub X. Find the period that the moon goes around the planet in. What you would want to do using this formula is the radius is your average distance, and the period you're looking for is roughly equal to that if you square it. And in order to solve this, you take the square root of both sides. So the period equals the square root of the radius to the third power. Not the radius, the radius of the orbit distance here to the third power. So here's a graphical version on, zoom in, don't switch, zoom in, zoom in. Pinch to zoom should be working. Bear with me for a little bit. Yeah, well, for some reason it's not letting me. There we go. But it will do it on the trackpad. So let's take a closer look at this. So orbital period squared in years squared on the vertical axis, and average distance from the sun cubed on the horizontal axis. By making these axes horizontal and vertical in this way, we're getting to see this as a straight line. It makes it look like a straight line function. It shows that Kepler's third law, p squared equals a cubed, holds true. And that's because when we do this to the axes, we get this nice linear relationship. This graph, based on Kepler's third law and modern values of the planetary distances, here we have average orbital speed and average distance from the sun. Notice the further away something is from the sun, the slower it goes. So going from Mercury to Venus, we drop from about 47 kilometers per second down to 35 kilometers per second, Earth at about 30 kilometers per second, Mars at a little less than 25 kilometers per second, while Saturn way out there orbits at less than 10 kilometers per second. And that's at a distance about 9.5 times the average distance from the sun of the Earth. Remembering an astronomical unit is about the average distance between the sun and the Earth. So now pinch to zoom is working. So think about this question. Can you answer it? about 8 years. So we need to find p, so p squared equals a cubed. Because a equals 4, a cubed equals 4 to the third power is 64. Therefore, p equals 8. P squared equals 8 squared equals 64. How did Galileo solidify the Copernican revolution? So he overcame major objections to the Copernican view. For example, the idea that Earth could not be moving because objects in the air would be left behind. With Galilean relativity, he proved that not to be true. Non-circular orbits are not perfect, as the heavens should be. And if the Earth were really orbiting the Sun, we'd detect stellar parallax. Galileo's experiment showed objects in air would stay with a moving Earth. For example, if you're sitting in a cart being pulled by a horse and toss a ball up in front of you, the ball moves with you. Objects will stay in motion unless a force acts to slow them down. This is usually thought of as Newton's first law of motion, or the law of inertia. Tycho's observations of comets and supernova already changed this idea that the heavens were perfect. Using a telescope, Galileo saw sunspots on the sun, imperfections in the holy golden disk, mountains and valleys on the moon, showing it's not a perfect sphere and that it's a place you could go to and walk around if you could just get there. Tycho Brahe thought that he had measured stellar distances, so lack of parallax seemed to rule out an orbiting Earth. Galileo showed the stars must be much further away, in part by using a telescope to see the Milky Way as countless individual stars. If stars were much further away, the lack of detectable parallax was no longer so troubling. He also saw 4 moons orbiting Jupiter, proving not all objects orbit the Earth. In fact, with a program for your phone called Google Sky and the camera in your smartphone, even if it's not a great camera, this was doable 6-7 years ago, you can actually view the large moons of Jupiter. They're not big, beautiful pictures, they're little tiny dots. You have to take the picture, zoom way in on it, and see 4 or 5 little dots, but they're there. Galileo's observations of phases of Venus prove that it orbits the Sun and not the Earth. In 1633, the Catholic Church ordered Galileo to recant his claim the Earth orbits the Sun. His book on the subject was removed from the Church's index of banned books only in 1824, and he was formally vindicated by the Church in 1992. All because he contradicted some ideas due to basically pagan philosophers, really. So how can we distinguish science from non-science, and what is a scientific theory? So science can be surprisingly difficult to define. Science means knowledge, but not all knowledge comes from science. So here's an idealized version of a scientific method. You make some observations, ask questions, suggest a hypothesis or a possible answer to your question, make a prediction, perform a test, experiment, or observation to see if your prediction holds true. If the test does not support your hypothesis, make another hypothesis, make a prediction, and test it. If the test supports your hypothesis, make another prediction from that hypothesis and continue testing it. Science is never completely certain and never always done. Science is always trying to refine itself. A hypothesis is an educated guess. This is what sort of a layman sort of a layman's theory right here. So when so hard to write vertically. When the average person says they have a theory about something, they mean really they have a hypothesis. They have an educated guess based on experience. That's not what a scientist means by a theory. It's much more than a guess. Sometimes we start by just looking, then coming up with possible explanations. Sometimes we follow our intuition rather than a particular line of evidence. Modern science seeks explanations for observed phenomena that rely solely on natural causes, progresses through the creation and testing of models of nature to explain observations as simply as possible. A scientific model must make testable predictions about natural phenomena that would force us to revise or abandon the model. The word theory has a different meaning in science than in everyday life. A science theory is not the same as a hypothesis. A science theory must explain a wide variety of observations with a few simple principles, be supported by a large, compelling body of evidence, and not have failed a crucial test of its validity. So, for example, Newton's laws are together a theory. But a theory never becomes a law of science. Newton's laws of science as a system together, as a theory, explain 90% of the physics you see around you, everything from the fall of an object to the orbit of a planet. But Newton's laws, collectively, will never become themselves a law. We'll never have Newtonian physics as this law that then has, I don't know, 3 sub-laws to it. We have the theory of Newtonian physics that contains certain laws. Now, that theory was actually superseded by Einstein's relativistic theory of physics, which contains statements which simplify to Newton's laws. So a theory can be superseded, but laws, they're things which have been proven by so much observation. Usually they are simple mathematical relationships that any new theory must incorporate within its body. Darwin's theory of evolution meets all the criteria for a scientific theory. Why do you think that? Pause and give your answer. After more than 100 years of testing, Darwin's theory stands stronger than ever. So there's never been a situation that couldn't be explained by Darwin's theory. For example, COVID-19. In all probability, it was not engineered in a lab. We don't have the knowledge to do that kind of thing just yet. But it evolved from a related bat virus, which, because of just the sheer numbers of bats and people, probably jumped from a human to a bat in the wild, spread around for a while, and then was detected in Wuhan, China. It's also just possible maybe it was being studied within a lab animal, but that's a different sort of topic. I'm not an expert on anything like that. That's just a pertinent example. Microevolution we've definitely observed. Macroevolution, like say, a type of horse evolving into a different animal altogether, that takes very long spans of time because the time between generations is so long. For example, human evolution takes so long because human beings are long-lived. Great apes, like our close relatives, ancestors, and technically ourselves, are long-lived creatures. So human evolution takes millions of years. We can distinguish science from non-science because it seeks explanations which depend solely on natural causes. A scientific theory is a model that explains a wide variety of observations in terms of a few general principles. So, Chapter 4, Making Sense of the Universe, Understanding Motion, Energy, and Gravity. So, describing motion with examples from everyday life. How do we describe motion, and how is mass different from weight? So, how do we describe motion? Um, in physics, which astronomy is sort of all tied together with, is the discipline of astrophysics, we use a type of math called vector math. So you throw down a coordinate system and you can draw an arrow from the origin to a particular point. So the reason we use vectors is because, let's say this arrow represents Earth's motion and this arrow represents a comet. If these arrows are pointing this way, one thing hits the other. If they are parallel to each other, they never hit. If they're at some angle like this, they're going away from each other. In real physical situations, you don't just need to know how large a number is, you need to know what direction things are moving in. That's why we use vectors. So position, with the little arrow on top, the position vector, the location of an object in three-dimensional space. Time, on the other hand, the sequence of apparently simultaneous events, is known as a scalar. So position in three-dimensional space is a vector. It has directionality to it. Time is just a sequence of events. You can write a vector like so, using ordered pairs or ordered triplets in three-dimensional space. Or you can use what are called unit vectors. And these vectors can be represented in different coordinate systems, such as polar coordinates. Here I show a relationship that gives you the same vector in both polar coordinates and also rectangular coordinates, xy coordinates. The length of a vector in two-dimensional space is basically an expression of the Pythagorean theorem. In three-dimensional space, you just add one more number to all of the above. So speed is change in position and scalar. So it's change in position scalar with respect to time. Whereas velocity is the change in your position vector with respect to time. Velocity is a vector, speed is a scalar. So d gives us the distance there. Here I'm giving you the formula for three-dimensional space. X final minus x initial squared plus y final minus y initial squared plus z final minus z initial squared. Example, drive 10 miles in 1 hour. Your speed is 10 miles per hour. If there was a vector symbol above that, that would be velocity, which is a vector. So velocity is the change in position vector with time. X final vector minus x initial vector over time final minus time initial. You can see how the direction definitely matters when it comes to cars. This will also be written as delta x over delta t. For a few of you who do know calculus, and there are a few in this class who know calculus, taking the limit as delta t goes to 0 of delta x over delta t gives us the derivative of position with respect to time, which is also velocity. If you don't know calculus, don't worry. I'm just including this for the people who do. Precise definitions to describe motion. Acceleration, A, the change in v with respect to time. So acceleration is the change in velocity with respect to the change in time, delta v over delta t. For example, this luxury car goes 0 to 60 miles per hour in 2.6 seconds, like you might see in some commercials. That's an expression of acceleration. Tensors, scalars, vectors, and higher rank tensors. So reviewing, a scalar is a quantity with physical size or magnitude and no direction. So the mass of a meteor is 50 kilograms. A vector is a quantity with physical size and direction. De Sears Tower is 6 miles to the southeast. A tensor is a quantity with a different magnitude in every direction. For example, gravitational waves are tensor waves. For now, we only need scalars and vectors. We'll talk about gravity at the detail of needing to at least qualitatively discuss tensors later in the course. Given a vector, position, velocity, or acceleration, one can make a scalar using something called the dot product. So, for example, the scalar, written as the magnitude of x, that's what those double bars mean, means taking the dot product of x with itself and then taking the square root of that. And how do you do that? This shouldn't be plus, there should be a dot. So this works out to a squared plus b squared. Notice this looks a lot like the Pythagorean theorem. See? Like there's a little, it's like we have a little triangle right here. The right triangle. A squared plus b squared is equal to c squared. Yeah. In fact, let me go ahead and correct this while I'm here. When I originally created these slides, I was in the middle of giving a lecture, and sometimes when one is hurrying, one makes mistakes. Getting the animation sequence on that one right. Anyway, acceleration of gravity. So all falling objects accelerate at the same rate, ignoring air resistance on Earth. About 10 meters per second. To be more precise, 9.80 meters per second. Speed increases by about 10 meters per second with each second of falling. For constant acceleration, the position vector is 1/2 acceleration times time squared plus initial velocity times time plus initial position. Velocity at any given point in time is the acceleration times time plus the initial velocity. And the acceleration as a function of time is just a constant. For the few who know calculus, if you don't know calculus, do not worry about other people knowing a bit more. It's okay. V equals d by dt of x of t, and a equals d squared dt squared of x of t, or the second derivative of position with respect to time, which is the first derivative of velocity with respect to time. So this Apollo 15 demonstration, this is a video, which, do I have it in video form here? No, I don't. But basically, we'll actually watch this when class is live and talk about what he does. He drops a hammer and a feather in the vacuum or near vacuum of space, and they hit the ground at the same time. Momentum and force. So momentum is mass times velocity. A net force changes momentum, which generally means acceleration or change in velocity. Net force means the sum of all the forces acting on a body. So momentum is a vector, mass times velocity. The change in momentum with respect to the change in time is force, which is equal to mass times acceleration. Net force is the sum of all the forces pointing in every direction. So if this vector is one force, and this vector is another force, then the net force will be, let's say, this vector. Sort of, well, maybe not like that. So not precisely, but you'll see. Here I show an example with a net force where we have F1 pointing in one direction, F2 pointing in the other direction, and the net force is F1 plus F2. If F1 and F2 are equal in magnitude and opposite in direction, they cancel each other out. So how do you add vectors? You can add any number of vectors by drawing them head to tail. For example, these three vectors. If I draw them so they're all lined up head to tail, and then draw from the tail end of the first one to the head end of the third one, the result is the sum of all those vectors. And it doesn't matter the order you do it in, the result will always be the same. And it's okay for the vectors to cross each other. And again, doesn't matter the order you do it in, it will still work. It's always more precise and simpler in the end to use algebra. Doing it graphically involves carefully measuring with a ruler and a protractor, and it's really easy to make a mistake. But with algebra, you write all three vectors in the same coordinate system, figure out what the components of each vector are, add the components together by combining like terms, and you get the answer. For example, let F1 equal 2.0 newtons in the x direction. That's what I hat means. F2 is negative 1.5 newtons in the x direction, plus 3.0 newtons in the y direction. And F3 is 2.0 newtons in the x direction minus 1.5 newtons in the y direction. Combining like terms, F1 plus F2 plus F3 is 2.0 newtons I hat plus 1.5 newtons I hat plus 3.0 newtons J hat plus 2.0 newtons I hat minus 1.5 newtons J hat. This is confusing because you haven't had a chance to practice any of it. But if you go through the tutorials and problems in the book, you will see that. F equals 2.0 newtons minus 1.5 newtons plus 2.0 newtons I hat plus 3.0 newtons minus 1.5 newtons J hat. So adding all of those like terms together, 2.5 newtons I hat plus 1.5 newtons J hat. So everything that has an I hat gets added together. Everything that has a J hat gets added together. But what are I hat and J hat? They just tell you what direction it's in. Take a minute and ask yourself yes or no about each of these objects and situations. So how is mass different from weight? This can be really confusing because we weigh an object in order to figure out its mass. So we weigh an object in order to figure out its mass. So that makes it very confusing. Also, in common speak, in countries where they use the metric system, if you ask someone their weight, they'll give you their mass in kilograms. So mass is the amount of matter in an object. It's how much is there, whereas weight is the force that a scale measures. Scales are calibrated so that when nothing's on them, they'll give you a reading of 0 kilograms. And then when when mass is put on top of them, that weight is used to figure out how much mass there is. But mass would be the same even in space, where there is no gravity. So on the moon, you weigh less, but your mass is the same. So there is gravity in space, but what the astronauts at the space station, for example, are in is a constant state of free fall. Orbit is like falling around the Earth, but you're going so fast in one direction that you never catch up to the Earth. Now for Newton's laws of motion. How did Newton change our view of the universe? What are Newton's 3 laws of motion? So he realized the same physical laws that apply on Earth also apply in the heavens. He discovered laws of motion and gravity and did experiments with light, invented the reflecting telescope, and also calculus. He was the Lucasian professor of mathematics at Cambridge University, a post recently held by the famous scientist Stephen Hawking. Newton's first law of motion: an object moves at constant velocity unless a net force acts to change its speed or direction. Objects in motion will remain in motion along straight line paths unless acted upon by an outside force. That is the law of inertia. No net force, no acceleration. In other words, a straight line where velocity is the slope. Newton's second law: force is mass times acceleration. For constant mass, F equals ma. A situation where the mass isn't constant would be like a rocket. It shoots fuel at the bottom, and it goes up. Newton's third law of motion: for every force, there's always an equal and opposite reaction force. So this is, again, an example, no constant mass, but it is a good example of Newton's third law. For every force, there's always an equal and opposite reaction force, and that reaction force gives the rocket its thrust. So mass times acceleration equals velocity times the change in the velocity of the thrust times the change in mass over the change in time. So given Newton's laws, is the force Earth exerts on you larger or smaller or the same as the force you exert on it? Every action causes an equal and opposite reaction. You press down to Earth, the Earth presses up on you, and they cancel each other out, so you don't go flying up. So which of these are true and which are false? The force of the car on the truck is equal and opposite to the force of the truck on the car. True. The momentum transferred from the truck to the car is equal and opposite to the momentum transferred from the car to the truck. True. The change of velocity of the car is the same as the change of velocity of the truck. False. The truck doesn't get moved nearly as much as the car. Remember Newton's 3 laws of motion. And that's it. So we are going to go into much more depth about all this type of stuff in the remainder of class. I'm also going to review basic algebra on our next class day. and I hope you get something out of this video lecture.